Uh, Souvik, am I audible?
Yes.
Okay. So we will wait for 1 or 2 minutes, then we will start. Okay. So let the other join. Okay. Good afternoon, everyone. My name is Devashish Panda. I am a research scholar and Prime Minister Research Fellow at IIT Guwahati. So this semester, for the course Structural Vibration, I have been allotted as a PMRF TA, and every Saturday from 3 to 5 p.m. we meet and conduct the interaction session. Actually, what we do, we go through the concept of the current week, then we solve different kind of problems which will be useful to solve your assignments of the current week through pen and paper. Also, we solve different examples using MATLAB. And after each recording sessions or each interaction session, you will get the recording video, solved assignments, and the MATLAB scripts. So today, actually, we will go through the variational calculus. So mainly the Hamiltonian principle and Lagrangian equation, how we can use them to solve different dynamic systems. We will see. So we will first start with the general coordinate system. Then we will see the general SDOF system. Then we move to Hamiltonian principle. We will develop the Lagrangian equation from Hamiltonian principle, and we will see different form of variational principle like Euler's first and second equation, also Hamiltonian equation, Hamiltonian colloquial equation, and all these things. So we will see. So let's start like today's session. So recall till now what we have you know learned from this course, or what we have solved during these interaction sessions. So basically we have solved a SDOF system under different kind of loading. Say we have solved the single degree of freedom spring mass damper system, which is subjected to some harmonic force, or say this f of t. We have solved that f of t for harmonic force. Say it can be some sinusoidal force or some force in terms of cosines, so harmonic force. Then we move to arbitrary force. Using Duhamel integral, we have solved how to we have seen that how to solve this response of a SDF system using that Duhamel integral, and also different kind of step and pulse forces we have seen. And on the last interaction session, we have also seen that response spectrum. And also there also we have seen that response spectrum is nothing but the maximum responses of a single degree of freedom system as a function of time period Tn for a fixed value of Ji and for fixed earthquake motion. So the thing is, till now we have solved different problems regarding the single degree of freedom system, but most of the dynamic system may contain more degree of freedom system than single degree of freedom system. Say for example, we have a 3-story building. So this three-story building can have the degree of freedom say x1, x2, x3, say because it will have say mass m1, m2 and m3, and also the stiffness property for a different story will be different, and if damping is present there, then damping will be different for different stories. So the question is, or the thing is, like we have till now we have solved different kind of problems associated with single degree of freedom system. Now how to solve with when we have multiple degree of freedom system, we will see during the course. Like we will start from today is the theme of this, like how to solve this multi degree of freedom system. So this will start. So first, before going there, this course actually content the variational principle. So today we will discuss that how to form Lagrangian equation, how to solve different kind of problems using Lagrangian equation. Even we will go through that energy approach, how to solve using that either conservation of energy law or virtual displacement law. All these things we will see. So first, let's try to understand what do you mean by say generalized coordinates. So we know what do we mean by say degree of freedom. Already we have defined the degree of freedom. It's the minimum number of independent coordinate required to describe the deformed shape, or required to describe the position of the mass corresponding to its original position. Okay. So now if we look carefully this example of pendulum. So we started with that pendulum problem. So let's quickly go through it. So it has a bob, some mass it contain, and say for example this bob is attached to a, say for example, rigid string which is not extensible for now. So what will it do if we give it some displacement? It will start swinging along this coordinate system. So here we can see that bob is in physical coordinate system, or we can say in Cartesian coordinate system in x and y. So the physical system present, generally we represent the physical system with respect to the Cartesian coordinate system, say x and y. So this coordinate system we call the physical space of the dynamic problem or the dynamic system, the Cartesian coordinate. Now, once we have defined the Cartesian coordinate, and from here the definition of the degree of freedom, we can say for this pendulum the degree of freedom will be 1, and that is theta, because we can see at any point this x and y is not independent. Actually it's constant by a condition which define like x square plus y square is equals to l square, because the string is not extensible. So now we have a degree of freedom for this system is theta. So we already have seen how to solve this system. That means how to write down the equation of motion for this pendulum and how to solve for theta. That is my response, or theta dot or theta double dot, displacement, velocity and acceleration. What you want to calculate, you can calculate it. Now say for example this is the equation of motion for this pendulum. Already we have derived it, theta double dot plus g by l theta is equals to 0. That means it has a natural frequency omega n is equals to root over of g by l. G is nothing but the gravitational acceleration and L is the length of the cord. So once we can, you know, uh, identify the response, or we can calculate the response. We can calculate the response using different techniques we have seen. Either we can go with the numerical techniques where we have discovered that numeric beta technique or Wilson theta or OD45, whatever you want to use to solve the response, you can use them. So after solving the response, if you plot the response, we will get like time versus theta. If we plot, it will give this kind of response. So corresponding to that theta, that means the degree of freedom we have considered for this system, this space is called the configuration space. The configuration space. That means the space created by that degree of freedom, whichever we have considered for this system, is called the configuration space. Now here we can see we only need only 1 degree of freedom. That means theta is alone is enough to define the position of this bob at any time instant. So this is called the generalized coordinate or degree of freedom. Generalized coordinate, when we will use different degree of freedom, we will see that generalized coordinate term will come very often. So what we have learned or what we have discussed till now, because if we have a dynamic system, the Cartesian coordinate where the dynamic system is expressed is called the physical space of the dynamic system, and the corresponding degree of freedom or freedoms, if we consider the multi degree of freedom system, then we will have multiple degree of freedoms. Then this degree of freedoms we call the generalized coordinates, and the space formed by the generalized coordinate, that means your responses in which space or which coordinate system you are expressing your responses are called the configuration space. Now here we have seen that this motion of this pendulum is constrained by some condition, and this constant condition is associated with only x and y two dimension. So this kind of constant condition, if some system or some dynamic system poses or pursue this kind of constant condition, we generally define them as holonomic systems. Say for example, we have this two-story building. So this we call the shear building model. Say when we have seen the single degree of freedom system examples, we have modeled this building like this as a shear building model. That means this mass can move only this horizontal direction. It cannot move in y direction. That means the vertical direction. It has some stiffness and some damping, and we have modeled this as a shear building module. Now you can see if we have two-story building, so we generally have 2 degrees of freedom associated with that two masses. And we have for the physical system, we have some coordinate system that y, and this coordinate is x. So here also this x and y are called the physical space. And which are the generalized coordinates? Look here, x2 and x1t, x1t and x2t. These are the generalized coordinates. And the when we will solve this system and get the responses like time versus x1 of t, what will be the displacement? Say for example, we have input given some input xg double dot, then what will be the responses? Say for example, we will get this kind of responses, x1 of t and x2 of t, say t and x2 of t for 2 different degrees of freedom. We will have this kind of responses. So this space is called the configuration space. And also we have seen which kind of system we can define as a holonomic system if the you know uh, constant condition is associated with only that x and y coordinate system in Cartesian, obviously. Then this kind of system we can holonomic systems. Like here also this building we can say it has some constant condition and which is limited to its x and y coordinate, so it's also possesses this holonomic property. Now, so till now we have understood like generalized coordinate, when we will need that generalized coordinate, obviously when we will define multi-degree of freedom systems. And already I told you that this is the starting point of understanding and analyzing that multi-degree of freedom or the dynamics and motion of the multi-degree of freedom systems, because most of the engineering applications they are or they contain different degree of freedom or more than 1 degree of freedoms. That's why to understand and to analyze this kind of system, we need to know the basic terminologies. Okay, now for a dynamic system, how can we can apply this concept of the generalized coordinate system? So for example, for a dynamic system, if we plot the time versus the generalized coordinates, where we want to see like here x of t, x1 of t, x2 of t, if we make the plots of them, then try to understand like if a particle at t1 time instant, say for example its position is a, say for example its position is a, say it for a time instant t2 it will reach up to b. now the thing is which path the particle will follow. There are infinite number of possibilities of path it can follow. That means the problem is like how to optimize the path, or in a way how to optimize the response x of t or y of t in terms of this. So for that we need to, you know, first define the action integral. Action integral is nothing but it's like we will go into these things today. So just for now, just uh, the definition of action integral we just define as like from t1 to t2, or that two time instant we need to consider in between. And this action integral actually depends on two things. One is your kinetic energy and one is your potential energy. That means in a way it will depend on x, the displacement, the velocity and the time. So it's a functional and this is called the Lagrangian. We will see how to use that Lagrangian to form that equation of motion and to get different quantity, or particularly the expression for natural frequency. So the Lagrangian, which is a function of x, x dot and t, is expressed as t minus v, where t is nothing but the kinetic energy and v is the potential energy. So if we have a dynamic system, we can easily quantify the kinetic energy and the potential energy based on the response quantities which that poses due to that input. So that action integral and the Lagrangian concept will actually need to define or to understand the Lagrangian and Hamiltonian principle. So starting with the Hamiltonian principle says like if we have this kind of condition, so where we need to find out the optimum path which a particle follow from A to B. So the Hamiltonian principle says for a conservative and holonomic system we know, conservative system where you know the energy, total energy is conserved, like no loss of energy is occurring at that system. So motion between T1 and T2 follows the path which action integral is stationary. Which action integral is stationary. That means it's nothing but the first variation is 0. So we can write it down like del I is equals to 0, and I already we defined the action integral. So del of say T1 to T2 Lagrangian of dt is equals to 0. That means now we have an idea like which path will give us the optimum solutions, or the solutions which we are looking for to quantify different parameters or different quantities or different responses of a dynamic system. So obviously about the action integral we have identified what how yeah please mute yourself. Yeah, thank you. So that means what we need to do, we need to, you know, we need to look for the stationarity condition for these paths, like the first variation will be 0. So we will understand these things in detail, but for now, like if we have a system and using the concept of like virtual displacement, how we can derive the equation of motion, and the concept of the equivalent mass, equivalent stiffness, equivalent damping, and equivalent force, how we can derive and how we can get these formulas for it. So first we will cover this section and then we will again go to this Hamiltonian principle and we will derive the Lagrange equation. So from here we will get the, from this exercise we will get the idea about the generalized degree of freedom system. Like I have said, the equivalent mass, equivalent stiffness, and equivalent damping. That means equivalent to the generalized single degree of freedom system. Say, for example, we have taken the same example what your course instructor had solved. So first we will go through this example and we will try to understand how we can get the equivalent mass, stiffness, and equivalent force for a dynamic system. So here The problem is simple and straightforward. We have a beam, rigid beam. So the beam has a total length 3L, because up to this hinge portion it has a length L. Then it has a spring at a distance L by 2. Again, it has a damper and spring L by 2 and L by 2, and one triangular loading is applied on this system. So this part is L, this is L by 2 from the hinge, this is again L by 2, and this is L. So total the beam has the length 3L. So what will happen due to the action of this dynamic loading? What will happen? Obviously, this beam will, start up and down or rotating with respect to this hinge. So if we draw the free body diagram of this system, so what will we see? So let's see, this is the position of the beam after getting a rotation theta due to the applied load. Okay. So now recall the way we derive the equation of motion uh, using the free body diagram. So first we need to identify the forces and displacement at each point, and then we can simultaneously formulate the equation of motion by combining these forces uh, in one equation. So first let's see, it has a rotation theta. Okay, just say this line we have a rotation theta due to this application of load. So what will be the displacement at this end? Say for example this end is A, at this end A. So if theta is small, obviously the displacement will be L theta at that point here. So what will be the displacement at the other end here? So from the hinge, the distance of this other end is nothing but 2L. So this ordinate will be nothing but 2L theta. Great. Now here, starting from here, what we will have at that point, the CG of the triangular loading is applied. That means passing through. So what will be the intensity of the force if we want to look here? So F of T is the intensity of load, and half of the load is acting here at the CG. That means L by 2 or half into F into L will give me the intensity of force there, and how much this portion will deform due to the theta rotation, because this distance up to this distance from the hinge is nothing but 3L by 2, because L by 2 and this is the center point for this, so 3L by 2. So 3L, and again, so this is the length 3L by 2 and the small rotation theta. So the ordinate of displacement here will be nothing but 3L theta by 2. Simultaneously at the spring force, obviously we will have that the deformation at a distance L from the hinge. So it will nothing but L theta. And what is the value of force? Obviously K, spring force K multiplied by the ordinate here theta. Now here at that point we will have a rotational inertial force due to rotation. So that is nothing but I into theta double dot. Why I am writing theta double dot? Because here only the theta is the degree of freedom we are considering to formulate the equation of motion of this system. Okay. Now again another force we have here is the inertia force. And inertia force, that means nothing but your am theta double dot. So for this system, say it's a continuous system, and we have considered that m bar is the mass per unit length. Mass per unit length. So the total length is 3L. So what will be the total mass for this system? That will be nothing but 3L into m bar. M. So this is your m into, for this coordinate you have seen that this is nothing but at a distance L by 2, so L theta by 2. So ultimately if we double derivative it, so it will get the 3m L by 2 theta double dot will be the inertial force due to this action. Now from this free body diagram we can easily derive the equation of motion for this system, but if we want to use the concept of the virtual displacement, because it will lead to you a one important concept how we can get the equivalent mass, equivalent stiffness, and equivalent damping properties. So what we will do, we will use here the virtual displacement concept. So what will we do? Generally we will provide a virtual displacement, the little displacement, the dotted line, after getting that or after giving this del theta over here. So we need to write the forces multiply with that del theta is equals to 0. That is nothing but the principle of virtual work. So starting from the that inertial force I theta double dot multiplied by the small variation plus, here we have the inertial force due to the mass, that means that 3m L by 2 theta double dot portion, and we have the virtual displacement d theta, and the ordinate of this portion is L by 2. Similarly, for the spring portion, spring force is nothing but KL into theta. It is acting at a distance L from the hinge, so L and the virtual displacement. Likewise, for the damping force is acting at a distance L by 2, so C L by 2 theta dot is the damping force, and multiplied by the displacement, and the ordinate here is L by 2 because it is situated at a distance L by 2 from the hinge. And for the external force, so this all acting on the downward side, and is equals to that says that equals to your ft. So obviously L by 2 ft into the ordinate of here is 3l into 3l by 2 into del theta. Now after simplifying it, very straightforward, like you just need to take out this variation or the small displacement outside and just simplify it. So for the theta double dot term, arrange the theta double dot term and take it outside the bracket, the theta double dot. So we will left with I plus 3 by 4 L cube m bar. M bar is nothing but not the total mass, is mass per unit length, plus L square by 4 C theta dot plus L square K theta minus 3L square by 4 Ft is equals to 0. Now this small displacement, whatever we have provided, it cannot be 0, because for this displacement we are getting this dynamics of this system. So obviously if this cannot be 0, the rest of the part will be 0. Now if the rest of the part will be 0, we can simplify and write it down like this. So ultimately look what we actually getting, we are getting like m theta double dot plus c theta dot plus k theta is equals to some force in term. If we want to simplify this equation like this, so obviously here this is nothing but the mass term, this is nothing but your total C term, and this is your K term in a simplified manner, and this is your F term, right? So now if we want to write down the natural frequency of this system, what will be that? Wn is nothing but under root of K by M. So total this counter for the K part, and this is counter for the M part. So we will easily get it like L square K by I 3 by 4 L cube m bar, and I we can easily calculate like 1 by 12 ml square. So m we know total mass and total length of the beam, we can calculate the I. So by this way we can easily find out the natural frequency, like if the mass per unit length, if the stiffness of this spring, if the damping constant of the damper, and the intensity of load, all the values are provided, we can easily calculate the natural frequency of this system. Now once we have the natural frequency of the system, rest of the design, like from the response spectrum as per this damping and the natural frequency, or natural frequency we can convert it into time period, corresponding maximum displacement we can find it out, and we can proceed with the design. Now what I said, like here we are trying to get the concept of the equivalent mass, equivalent stiffness, and equivalent damping properties. So how we can get them, so we will just see in a minute. Like here also you can see from this equation, so this term is nothing but implying the equivalent mass of the system. This whole term like c multiplied by l square by 4 will counter for the equivalent damping, and this is for equivalent stiffness. Now that equivalent term we will quantify in a different manner with respect to the shape function, because ultimately when we will deal with the multi-degree of freedom system, we will have different kind of shapes or shape function with respect to different natural frequencies, which we call that mode shapes and all these things. So we will see later. But first, like if we have a cantilever beam like this, and if it is subjected to a UDL, entire UDL across its entire length, it has a length say for L, and it has a UDL for the entire length. So how we can get it? Say for example, if we want to now recall the definition of the degree of freedom. If we want to specify the deformed shape of this cantilever beam, so how much or how many degree of freedom we need? If we consider all the points, so obviously all the points will possess some mass, and with respect to all the points we need to consider the degree of freedom, say infinite number of degree of freedom we need. So which is actually not possible to do, because it is possible but it will be time consuming and also um, computationally computationally heavy thing. So how we can um, simplify this equation with respect to some shape function. Shape function, how we will get the shape function, how to derive the shape function, we will see in step by steps on the later I think 8th or 9th module you will get it. So for now, let's consider we have this cantilever beam, and some force UDL F x comma t is acting on this system, and my deformed shape y x comma t is the deformed shape. Like we all know, if cantilever beam is subjected to an UDL, the deformed shape will be like that. That means we will have a quadratic equation or quadratic function which will describe the deformation at any point. So now, if I want to describe this deformed shape with the help of separation of variable, we can write it down like phi of x into y of t. That means function of space and function of time. So this phi of x is nothing but we call it the shape function, and y of t is like your response of this system. So that phi of x, obviously, the shape function should define your deformed shape. That means, look here, the deformation at this point A and this point say B, say obviously, if we want to quantify the generalized mode shape or generalized shape function for here, so phi of x at x equals to 0, obviously it will be 0, and phi of L, that means at x equals to L, it will be 1. So that are the basic properties of the shape function we will see. Like when we will talk about the mode shape, the generalized mode shape, normalized mode shape, normalized mode shape, all these things we will see these things. For now, say we have you know we have expressed the deformed shape of this cantilever beam as a function of shape function, that means as a function of space and as a function of time. So now, if I want to calculate the kinetic energy of this dynamic system, what will be that? So kinetic energy is nothing but half, say 0 to L. This is your cantilever beam. So obviously we need to integrate it, because that we are not considering that lumped mass thing. Otherwise, we can write that half m into v square if I get the total mass and all these things. So half into m of x. This m of x is nothing but m bar of m bar, that means mass per unit length. Great. And so half, generally what we know about kinetic energy, it's nothing but a half m into x dot or y dot square, right? So here, instead of that, what we have how we have expressed like half into m of x, because we are expressing as mass per unit length and using the deformed shape whatever we have considered, that y dot of x comma t square dx. Now if we simplify it, y dot square x comma t we have expressed in the term of two variables, one corresponding to the space like shape function and one is the response. So just we replace it here, and again if we simplify it, what we'll get? We'll get half m of x phi square x dx, this term, into y dot square of t. So now if we further simplify it and write it down like this, half into m equivalent into y dot square, this is your kinetic energy. And this m equivalent, just see, within that integral part we have m of x phi of x squared dx. Now for a system, for this kind of systems, say for continuous systems also, if we have the mass per unit length m bar value or m of x value, and if we know the shape function phi of x, how it will deform, like here I know the shape function, I can express this in the term of x, because I know at the fixed end the deflection will be 0, at the free end the deflection will be maximum. If I normalize it with respect to 1, so my shift function will be 0 at a and 1 will be at b. So I can propose any kind of sinusoidal function which will um, satisfy these two boundary conditions, then I can use it as a shift function. So for now, what will be the equivalent mass of a continuous system if we have the mass per unit length and the shape function associated with that dynamic problem? We can easily calculate the equivalent mass. Now this concept is important when we will actually generalize the multi-degree of freedom system as a single degree of freedom system, and we will try to calculate the natural frequency to understand what will be the deformed shape and what will be the responses associated with that dynamic problem. Then we need to use that. So equivalent mass for a system, how? Mass per unit length multiplied by the shape function integrated over the total length will give us the equivalent mass of the system. Now, similarly, if we look into the potential energy nothing but V is equals to, what do we know, half into, okay, here already I have defined like half into k into x square. Why? This is coming from the restoring force. Yeah. So half into k into x. Now, what do we need to do here? Like for this thing, if we simplify the equation with respect to like moment at bending moment at different locations, say for example, uh, for this system we have the mass per unit length property, we don't have the total mass and total stiffness, so we will write the equation in the form of half m into d theta. Now how, why I am writing that, half m into, so first thing, say if we have a beam problem, what is the relation between moment and the flexural rigidity? It's nothing but m is nothing but ei in d2y dx2. And now what is the relation between that curvature for the pure bending equation? It's nothing but d2y dx2 is equals to d theta by dx into mx by ei. Now from this equation we can easily calculate what will be the value of d theta. So d theta will be nothing but, say if we consider this portion only, so d theta will be nothing but mx into dx by ei. So now if we express the potential energy in terms of half into the bending moment and the rotational the curvature, then if we simplify it, what will we get? Like mass, moment, bending moment at, say, m of x, define your bending moment at a distance x. So obviously d theta, replace the equation of d theta from the equation of curvature and moment and flexural rigidity. So here d theta is nothing but m of x by ei into dx. Now if we further simplify it, what we'll get? M square, and m is nothing but ei d2y by dx2. So if you replace that, so what we'll get? Ei d2y dx2 whole square. So finally, what we will left with? We will left with potential energy V is equals to this term half 0 to L EI phi double dot square, because here we can see that if my y of t is the deformed shape, we can express is at phi of x and y of t. So what will be the dy by dx is nothing but dx. We are differentiating with respect to the space variable. That means phi dot to y. And again, if we differentiate with respect to x again, so we will left with phi double dot into yt. So here instead of this d square y d2y by dx2, we can write it down like phi double dot x y whole square ei at the front, and we have this term inside the integral. So if we separate this term, what we will left with, the k equivalent is nothing but 0 to L ei phi double dot x square into dx. So this is nothing but the equivalent stiffness of the dynamic system. Like what I said, like we know that potential energy, the potential energy V is nothing but a half k into x square, or if we have half k into y square, if we have the generalized coordinate y, then this. So look, the final expression what we have, similarly half k equivalent into y, because for this system y we have considered the generalized coordinate or the degree of freedom. So similarly, this k equivalent or this term ei double derivative of the mode shape the square dx will give us the equivalent stiffness of this continuous system if we generalize as a SDOF system. So once we have the equivalent mass and equivalent stiffness, we can easily calculate the first natural frequency of the generalized system. So now in a question, if your shape function is given, your say for example your EI flexural rigidity is given, and they ask like find out what will be the first natural frequency of the generalized system. So by this way you can calculate the first natural frequency of the generalized system, and you can get the value of m equivalent and k equivalent for this system. Now we can also further, if we want to extend it, we can also get the equivalent damping force too. Now how we can get the equivalent damping force, we will see. So for a spring mass damper system, we know that if C equivalent is the equivalent damping for this system, and C equivalent into y dot, what is that quantity? That is nothing but the damping force FD, right? Now, if we apply small variation with that, say del y, and integrate over the full length of the beam, what we will get? We will get the total damping force. So that actually expressed here. What is the total damping force due to small variation of del y? So this actually expressed in terms of y dot, like y dot, and we have dy. So that y dot x comma t, here we can see y dot x comma t, what will be the value, and what will be the value of del of y of t. So we can express this as a term of phi of x and del of y. That means one function of space and one function of time. And so if we solve it, so what we left with c phi, that means phi square x function of space into that small variation with length, because it's the function of length dx, and y dot and del of y. So now if I want to write it down, what will be this quantity from this equation C equivalent? So this comes as C equivalent is nothing but 0 to L C phi square x dx. That means if we have the damping constant C, the value of the damping constant, and the knowledge of the mode shape or the shape function, we can easily calculate the equivalent damping force, or the force which we required to which we required to diminish the complete energy, which we call the critical damping. All these parameters associated with the equivalent damping term we can calculate. Like here, we just simplified the equation to get the equivalent stiffness, mass, and damping with respect to two variables. One, with respect to this shape function, that means variable of space and variable of time. So from here, we can easily calculate what will be the natural frequency, and also for the external forces, we can also get the external equivalent force which is acting on this system. So for that, we need to you know um, reorganize the equation of the external work done. So for this system, if we want to say for any system, if some external loading is applied, say for example, if a cantilever beam and external loading is applied on the system, so obviously the external work done will be that force into dx. That means if we want to integrate it 0 to L f x comma t into dx, that will be the total force and into that displacement. Now if you further simplify this equation, what we will get, that del y, we just express this in terms of the space variable phi of x, that means nothing but your mode shape or the shape function, and the the variable y in time. So we will have that f equivalent. If we simplify this equation further, or if we rewrite the equation, not simplifying it, we are rewriting an equation. So it's nothing but we will get f equivalent into the virtual displacement, or the displacement whatever we provided associated with the dynamic system. So f equivalent is nothing but 0 to L f x comma t, again the variable associated with the space, and dx. So now we have identified what will be the M equivalent if we have a system. Say for example, if we have a system, one loading is applied, say this is my fx comma t. I know the mass per unit length, I know the total length. If I know the shape function of the system, can I, now the question is, can I identify the natural frequency or of this generalized system? Look here, we haven't considered any like point wise degree of freedom for this entire system. Instead, what we have done here, we converted that mass per unit length, stiffness, and all these properties with respect to the equivalent mass, equivalent stiffness, and equivalent damping properties, and from where, or even equivalent force quantities, and from where we can get the idea of the equivalent first natural frequency. Once we have the natural frequency, corresponding to that natural frequency, we can look for the response spectrum. What are the maximum responses with respect to that omega n, and for a particular value of xi, we can, xi, that means the damping quantity, whatever present in that system, we can identify, and as per that quantity we can get the responses of the system, and we can do the design accordingly. Now if we want to solve, like which kind of problems may come from this section, so if we quickly want to solve one example, say here we have a uniform tower of length L, length 8 meter, has a mass per unit length. Look, mass per unit length 85 kg per meter. Assume the shape function 1 minus cos pi x by twice L. Determine the natural frequency of the tower given EI is 4 into 10 to the power 6 Newton meter square. So how we can do that? Now we have the idea of the equivalent mass, equivalent stiffness. If we can calculate the equivalent mass and equivalent stiffness, we can easily calculate the natural frequency of this system. So what will be the equivalent mass? M equivalent is nothing but, we know the expression, 0 to L mass per unit length multiplied by the shape function square into dx. So we have the shape function phi of x is nothing but 1 minus cos pi x by twice L. So what I need to do, just replace this here and solve the integral. So here mass per unit length, the value of mass per unit length is provided 85, right? So ultimately, if we solve this integral, it's simple integral cos, cos is sitting over there. So we will have that mass equivalent is nothing but 154.36 kg. Please recheck the calculations. Now, what do we need to find out? We need to find out the generalized the equivalent stiffness. K equivalent is nothing but is 0 to L EI. What we need to do? We need to double differentiate that shape function and then use the value as a square and dx. So obviously, if we double get the double derivative of this shape function, what we will left with, we cos again become sine and again become cos. So we will left with like pi square by 4l square cos pi x by twice l. Now put these values here in a square term. Ei will be outside this bracket, and if you solve the integral, you will get these values. Ei already provided, L we know, L is 8 meter. Ei is provided as 4 into 10 to the power 6 Newton meter square. So the K equivalent comes as 23750 Newton per meter. So what will be the natural frequency of the system? Obviously the natural frequency of the system, or we can say the natural frequency of the equivalent system, will be nothing but K equivalent by M equivalent, and it comes as 12.404 rad per second. So by this way we can easily get the natural frequency of the system. Now further, if this question is further extended, like for a damping value of 2%, what will be the maximum response of this tower calculated from the response spectrum? Now we can easily calculate if we know the soil condition, if we know the value of damping. Already we have identified the omega n, so we can calculate the, or we can get the spectral displacement, spectral acceleration, all these quantities from the response spectrum, and we can do the design accordingly. Now, so till now, do you have any kind of questions? Okay then. So now let's say again we solve one another tutorial where like we will use that conservation of energy, this principle, to derive the equation of motion of a free vibration system. Free vibration, that means no damping will be present. That means the no external force will be present there. That means the system will vibrate with its fundamental frequency or natural frequency without any effect of the external force. So if we have a spring mass system and the degree of freedom here is x of t, that means it define the displacement of this system with respect to its original point or mean point. So we can easily write the kinetic energy. Kinetic energy T will be nothing but half m into x dot square. X dot, if x is my displacement, then x dot will be the velocity and x double dot will be the acceleration. So obviously the kinetic energy will be half m into x dot square, because x dot will be the velocity of this system, and the potential will be half into k into x square due to that spring force. So this can also be expressed as like 0 to x k in one dummy variable into dy. Now once we have calculated the kinetic energy and the potential energy, now we can have the total energy of the system. So now what will be the total energy? Just make the sum here. So this is the kinetic energy and potential energy. Now as per the law of, or the principle of conservation of energy, what we know, the total energy is constant. That means if we differentiate with respect to time, we will get 0. Now if we differentiate it with respect to time, what we will get? We will get like this equation. Say m x dot x double dot, because here we have half m into x dot square, so 2 will come here, 2 by 2 m into x dot square. Similarly this, and we can write the equation like this form, where mx double dot plus kx, within that bracket x dot we have just take it a common, equals to 0. Now obviously that x dot at any point cannot be 0, because if the velocity will be zero, then there will be no motion or no dynamic motion of the system. So we can left with this term that mx double dot plus kx is equals to 0. That means this nothing but the equation of motion which we derived using D'Alembert principle, using the um, mm, using the concept of that FDP, that means free body diagram with corresponding to energy principle. And also we have seen that using the conservation of energy we can see, or we can derive the equation of motion, and we can easily find out the natural frequency of a system. And that is which is actually very useful for our designer to design with respect to the dynamic behavior of the system. So that can be one approach to derive the equation of motion using that principle of conservation of energy. Now, if we want to further extend this, like if we have a system, vibratory system, and whose response is like by defined by whose response is displacement is defined by xt is equals to c sine omega nt plus alpha or theta. Like the recall this steady state response of any dynamic system or any SDOF system is nothing but x of t. We can express as the amplitude c sine omega nt plus some phase alpha or theta. So let's say we have a system where we have defined the displacement, or we get the displacement in terms of this. So obviously what will be the x dot is nothing but c omega n cos omega. That means what will be the velocity quantity of this thing, c omega n cos omega n t plus alpha. So what will be the amplitude of this response? It's nothing but c. The amplitude is c. That means if we have the response like this x of t, and this is t, say, so this is nothing but the amplitude. Okay. So ultimately, the what will be the velocity amplitude? It will be nothing but c omega n. Now what do we need to do? We need to calculate the kinetic and potential energy again. So what will be the kinetic energy for this thing? The kinetic energy T will be half m into x dot square, and the potential will be half k into x square. Now we have the displacement, we have the velocity. We can easily calculate the kinetic and potential energy for this system. If I know the amplitude of this vibration, if I know the omega n, if I know the phase lag, or we can consider the zero phase, and we can easily calculate the kinetic energy, or we can easily get the responses of the system. So if I want to calculate now, if I want to calculate the maximum kinetic energy and maximum potential energy, how we can do that? So the maximum kinetic energy will be half into m into the maximum velocity, or the amplitude of the maximum velocity. So here this is the velocity of this system. So we have here a same system previously, whatever we have defined the system, same kind of system we have. X. So obviously this is my velocity. So what will be the maximum velocity? Obviously the amplitude of it. So half n c omega n square. Now potential energy, what will be the maximum value of displacement? Obviously its amplitude c. So half into k into c square. Now if we equate the maximum kinetic energy to the maximum potential energy, what we will get? Look, half m c omega n square comes as half k c square. From here, if we simplify this equation, omega n square is equals to nothing but k by m, and omega n is nothing but under root of k by m. This method of finding the natural frequency of, or this method of processing one dynamic system, we call the relic method. That means this method actually started from some deformed shape. Then we need to find out the maximum kinetic energy and maximum potential energy, and then we need to equate them to get the natural frequency of the system. Say for example, if we want to solve this cantilever beam and want to get the natural frequency of the beam, or the first natural frequency of the beam, or the cantilever beam, how we can solve it. Say for example, here the length of the beam is L, and we have considered that the total force is acting on the free end. So if at the free end, if force F is acting, so as for the static analysis, we know the maximum deflection del will be nothing but FL cube by 3 EI. If EI is the flexural rigidity of the beam, and if M bar and M bar here is the mass per unit length. So now let's consider the deformed shape Y x comma t. Already you have seen that we separate this term, or we express this term using the separation of variable. One is phi of x, the function depend on the space, and y of t, that response. Now for this system, for the dynamic system, let's see the response will follow again the previous example of steady state, like c sine omega nt plus some alpha. So obviously what is that c quantity with respect to the dynamic deflection? That c is nothing but the amplitude of the motion. Now here from the static analysis we can see the maximum deformation can be FL cube by 3I. So that is nothing but your C in that dynamic quantity. So C is nothing but FL cube by 3EI. So now we have the response. We have the understanding of the response. Now we need to assume some shape function. Now from here we can see that we have zero deformation here and the maximum deformation del over here, or if we consider del is equals to 1, so 1 will be over here. So now let's say we consider a shape function phi of x is nothing but 3l square lx by 2 into x square by 6. Now if we want to satisfy the condition, say phi of x at x equals to 0, you will see it will give the 0 value, and phi of x at x equals to L, it will give the value of 1. And if we consider here the value is del, so we need to replace here a del. Then obviously it will give the value corresponding to that del. So we have now the shape function, we have now the response quantity. Now for the questions, the shape function and the response quantity will be given. And for the real purposes, we need to identify what will be the shape function. We will see when we will solve the problem related to continuous system. We can easily find out which will be the possible shape function for a particular dynamic case. So again, let's your deformed shape you express is in terms of phi of x into y of t. Y of t is nothing but c sine omega nt plus alpha. Okay, so once we have this quantity, we can easily calculate the y dot of x comma t, and that will be nothing but phi of x c omega n cos omega n plus alpha. Now what we need to do as per the Rayleigh method, because we need to find out the natural frequency as per the Rayleigh method. So what we need to find out as per the Rayleigh method, we need to find out. So first step, we have defined the shape function, we have defined the response quantity. Then what we need to do? So in second step, we need to calculate the value of maximum kinetic energy, maximum potential energy, and we need to equate them. So first we need to calculate the that value t, maximum value of tm. So what will be that? It's nothing but half m into dy, that means the mass per unit length into that segment, multiplied by y dot maximum square. So we'll get the maximum value, like in the previous example here we have solved it, half m into x squared t. So x is nothing but the amplitude of this thing. So here we have incorporated that phi. So phi value will be here. Now if we simplify this equation, what we will get? We just need to replace the value of phi over here. So phi is nothing but 3l by lx by 2 into x square by 6. So just put it here, and y dot, in place of y dot max, you will have only the value this, only the amplitude portion phi of x c omega n dot. So this portion is overwritten here. Now after simplifying this equation or this integral, we will left with that t max is nothing but 17 m c square omega n square by 80. Now what we need to do, as per the Rayleigh method, we need to calculate the Vm, maximum Vm, then we need to equate these two. So we know that V is nothing but half into k into x square. Now if we simplify this equation, we can write like is equals to half into v max, if we want to write it, that k into x, and we know force is nothing but k into x. So we just simplify the equation like this. So x is nothing but the displacement, and what will be the maximum displacement is nothing but the amplitude of this displacement c. So that's why it is written as f into c. Now already you have seen that maximum deformation at the free end will be FL cube by 3 and that is equals to my C. That means the amplitude of the displacement. Obviously, the maximum displacement will be from the static case. We can easily sense, or we can easily identify, or we can easily tell that the maximum deformation will be at the free end and the value will be FL cube by 3 So from here, now replace the value of F. So it will be half into 3 EIC square by L cube. Now equate Tm is equals to Vm. What we will left with omega n. The natural frequency of the system is nothing but 120 EI by 17 m bar L cube. Now for a given system, if for a given system the shape function phi of x is given, if I know the response quantity y of t or x of t, I can easily calculate, or I can easily identify the first natural frequency using the Rayleigh method. So how? First we need to consider the deformed shape, then we need to calculate the maximum kinetic energy, then we need to calculate the maximum potential energy, we need to equate them, we will get the formula or equation for the natural frequency of the system. Say for example, we have this example, how to solve it. So for now, do you have any kind of questions you can ask me? Sovik?
Yes.
Yeah. So clear is it? Or you have any kind of questions?
No.
Okay then. So we will solve few problems and then we will move to that Hamiltonian principle and Lagrangian equation, and we will solve few problems there also. So now from the Rayleigh method, it is clear that if we have this phi of x, if we have y of t, and if I can express my deformed shape like phi of x and y of t, we can easily calculate the natural frequency by equating the maximum potential energy to maximum kinetic energy. So now look at this problem. The displacement of a SDOF system is given as this. The displacement is given as, say, y of t, total displacement is given as 8 sine omega nt minus 0.78 centimeter, right? So from this equation itself, I can say that y max or x max, say, let's say this is x or y, you can denote it any notation, using any notation. So what will be the value of x max or c? The x max will be 8 centimeter, the amplitude of this motion, right? What is we need to find out the natural frequency. So I can now, what I need to do, I need to find out x dot of t2. So x of t is given. The maximum value of x, that means displacement, is nothing but 0.8 centimeter. This value is already given. Now x dot t, I need to differentiate this. So what will be the x dot t? X dot t max, actually if I want to uh, first we need to differentiate it. 8 into omega n cos omega nt minus 0.78. So what will be the maximum value of x dot t? The maximum value of x dot t will be this. So 8 here is in centimeter. We need to convert it to meter, because look at here, rest of the other units are provided in kilonewton meter. That means in meter. So the x max comes as 0.08 meter. If I differentiate this displacement quantity x of t is equals to 8 sine omega n t minus 0.78, so we will have 8 omega n cos omega n t, right? So what will be the maximum value of this x double dot t? That means the maximum value of velocity is nothing but 0.8, 0.08 omega n. 8 in centimeter, that means 0.08 into omega n, the c value, the amplitude of this vibration. Now once we have these two values, x dot max is equals to 0.08 omega n and x max is equals to 0.08. Now I can easily calculate what is my maximum kinetic energy, K max. I know half m into x dot max square. So x dot max I know 0.08 into omega n square. So we'll left with this equation 0.8 omega n square. Now what will be the maximum value of potential energy? Potential energy nothing but half into k into x max square. X max is nothing but 0.08. So we'll left with this. Now, as per the Rayleigh method, what we need to do, we need to equate maximum kinetic energy to maximum value of the potential energy. Now, if we do the equation and solve it, we will get the omega n as 0.244 rad per second. Great. So, this kind of problems may come during your examination, also during your assignments. So, let's say one more example regarding this. Say here, we have the displacement of a SDOF system. Again, the displacement is given. Say you can express this in terms of x or in terms of y. So 3 sine omega n t minus 0.78. We can easily calculate the x dot of t. Say 3 omega n cos omega n t. Why we need this two quantity? Because to identify the maximum value of x of t max and x dot of t max. So obviously what will be the value of maximum value of displacement is nothing but 3. This 3, the amplitude of this motion 3, that means 0.03 meter. Now what will be the x dot max? This is nothing but this 3 into omega n. So we have converted 3 centimeter to 3 meter. So 0.03 into omega n meter per second. Now what we need to do? We need to find out the Ke max. It will be nothing but half m x dot max square. So we have x dot max is equals to 0.03 multiplied by omega n, and this leads to this 6.75 into 10 to the power minus 2 omega n square. Now what we need to do, we need to calculate the maximum potential energy P half into K into X max square. X max is nothing but 0.03, so we will have 6.75 into 10 to the power minus 3. Please check the calculation once again, because there is unit error and unit variation. So that will lead to the erroneous answer. So now what we need to do, we need to equate Ke max equals to the potential energy max. So we will left with 0. Or 6.75 into 10 to the power minus 2 omega n square is equals to 6.75 into 10 to the power minus 3. So here from here omega n square comes as 0.01 and omega n is 0.31 rad per second. So by this way, for a system, if the shape function, if the stiffness and mass properties are provided using the Rayleigh method, we can easily calculate or we can easily find out what will be the natural frequency for the system. So for this, we just need to equate the maximum kinetic energy to the maximum potential energy, and then simultaneously we can calculate the value of omega n. So do you have any question till now? Sorry.
No.
Okay then. So till now what we have done, just quickly recapitulate it, and then we will move to how we can get the Lagrangian equation from the Hamiltonian principle. So first, like we have seen the concept of generalized coordinate system, the physical space, the configuration space, different constant conditions, and then we move to Hamiltonian principle, where we have seen that as per the Hamiltonian principle, the first variation is zero. That means the particle will follow the path of least action, we can say also. So before going there, we have solved a problem related to generalized single degree of freedom system, where we have the concept of equivalent mass, equivalent stiffness, equivalent damping, and equivalent external force. And if we have this equivalent external force, equivalent damping, and equivalent mass property, how to solve them using the shape function and the properties provided. And then we solved few problem related to this, like here we have solved a problem where the shape function ei and mass per unit length were given, so we get the value of natural frequency. And then we have seen that the equation of motion, whatever we have developed using D'Alembert principle, Newton's law, uh, and also that using the principle of virtual work, we can use the conservation of energy to get this response, or to get the equation of motion for this system too. Then we move to the Rayleigh method, where we have seen that if we can express our shape function with respect to deformed shape, if we can express the deformed shape with respect to these two variables, shape function and response of this structure, then we can also calculate the natural frequency for the system, provided we must know the shape function and the response quantity of the system. If we have or applied you know different kind of shape function which is not associated with the dynamics of the motion of this system, then we will get the erroneous results for this system. So using that Rayleigh method, we have seen that how to solve for a dynamic system, how to get the natural frequency of a system. It's nothing but starting with the generalized coordinate, that means and your shape function. Then you need to calculate the maximum potential energy, the maximum kinetic energy, and you can get the corresponding value of omega in there. And we have solved few example here. Now we will move to Hamiltonian principle. So the question is Lagrange equation. When we will solve that multi-degree of freedom system and even the continuous system, the Lagrange equation is very much important to solve this equation of motion. So first we will see that how we can get, or how using the concept of Hamilton's principle, how we can get the Lagrange equation, and using that Lagrange equation, how we can solve different equation of motion for a system. So recall, uh, you know, if we have a particle here, point A and point B, at time instant t1 and time instant t2. So the question were which path will follow this particle, or this particle will follow which path. So as per the Hamiltonian principle, it says that the first variation is zero. That means it will follow the path of least action. That means that that action integral will be stationary. That means the stationarity condition will be solved. So we have already seen that action integral is defined in terms of the Lagrangian, and Lagrangian will depend on, it's a functional, itself a functional Lagrangian, so it's depend on x dot, that means displacement, velocity, and the time. Obviously, because that Lagrangian L is nothing but T minus V. That means it's a function of kinetic energy and the potential energy. And we have seen that kinetic and potential energy are the function of x dot, and also time. So obviously that Lagrangian also is a function of x dot and t. And as per the Hamiltonian principle, the first variation, or the first variation of the action integral will be zero. That means del t1 to t2 L within that bracket x dot t will be 0. Now, if we want to expand it with respect to the generalized coordinate, so obviously we know that t, already I have said that t is a function of x and x dot, and also your v is a function of x. So now instead of x dot, these are also degree of freedom. If we want to quantify it with respect to qk, the generalized coordinate, we can write it like that: t is a function of q dot and v is a function of q, because half k into x square and 1 depend half into am into v square, so both are x dot square. So now if we want to simplify this equation, just that variation you just take inside that integral and just try to solve it. So what we will left with? We will left with del t and del v. Now if we want to further simplify this equation, we will have the form t1 to t2 del by del qk t minus v, because the del qk is there, here, and del qk is here, and just I am just taking the common del by del qk and delta qk. So we will left with t minus v, the t minus v plus this term, this quantity here, del t by del q dot delta of qk dot t. So here on the first term we have t minus v, and we know L is nothing but t minus v. So instead of t minus v, I am replacing the L. So this equation simplifies at del L by del qk, and here del qk and this bracket del t. And for the second quantity, what we will have? Del t by del qk delta qk dot dt. Now, further we will expand this second term using the chain rule, and we will see the final product lead to the Lagrange equation. So here the first term, the first part we will leave as it is for now. Now for the second part we will use the chain rule to solve it. That means the integration of uv rule. So this is the first variable dt by dq dot, and here on the second part we have d delta qk dot. So that delta qk dot is nothing but del of del t delta qk. This is actually written instead of this delta qk dot. So we have two functions. First function, we have second function. Now we can use that rule and do the integration. So let's simplify it and open up this integration. So the first part as it is. Now the rule applying, the first function integration of the second function. So this is my first function, this is the second function. So first function integration of second function minus integration of dt of first function integration of second function is equals to 0. Now if we simplify this equation, if we common it del qk into dt, because del qk into dt is all over the places. So for these two, if we consider the del qk dt and common it, plus we have left with this term del t by del qk dot. Now if we further simplify it, so we left with this equation. So integration t1 to t2 del L by del qk minus dt of del L by del q dot multiplied by delta q dt is equals to 0. Now obviously that delta qk cannot be 0, it's associated with the generalized coordinate system. So what we will left with? We will left with this term dl by dqk minus d dt of del L by del qk dot is equals to 0. And if we further simplify this, say I will have this equation d dt of del L by del qk dot minus del L by del qk is equals to 0. And this actually called the Lagrangian equation. And using this equation is very much important. D dt of del L by del qk dot minus del L by del qk, where qk is nothing but the generalized coordinate. And now from this equation you can see that we can have like qki 1 I2 I3. We can have, if we have different generalized coordinates for this system too, we can simplify, or we can use this Lagrangian equation to formulate the equation of motion and to solve the equation of motion. So from here we have seen that we just derived the Lagrangian equation from the Hamiltonian principle. Simple. We start with the action integral. Then, as per the Hamiltonian principle, the first variation is 0. Then we have written the kinetic and potential energy with respect to the generalized coordinate, and here we have considered that qk is the generalized coordinate. That means the generalized displacement. Obviously, qk dot will be the generalized velocity. And further, for the second rule, if for the second part, we expanded this thing and simplify it, and we have the final form d dt del L by del QK dot minus del L by del QK ddt of del L by del QK dot minus del L by del QK is equals to 0. This is nothing but the Lagrangian equation. Very useful equation to solve different kind of multibody dynamic systems in vibrational problem. Like if we want to solve one example using that Lagrangian equation, like this pendulum, we have derived the equation of motion using D'Alembert principle, using Newton's law of motion, using conservation of energy, using even we can generate it other methods too. Now we will see, using the Lagrangian equation or the Lagrangian function, can we derive the equation of motion for this system, or can we identify the natural frequency subsequently? Yes, we can do that. So how? So this is the again same problem we have taken. Like we have a simple pendulum of mass m. It has length L, inextensible. That means this cannot extend in that direction. That actually lead to that conclusion. Like we have only degree of freedom, generalized degree of freedom theta over here. And if this length is L, and if the circular path follows by this pendulum is S, and obviously that S will be nothing but theta into L if theta is very small. This is nothing but the curvature. Curvature we know, L into theta, theta into L. So from here we can have that S is nothing but the displacement. So if we differentiate it ds by dt, we will get the velocity d theta by dt. We will need it because we are going to calculate the potential and kinetic energy. So we have the displacement and velocity of this pendulum with respect to its position. Now what we need to do to formulate or to use the Lagrange equation, we first need to formulate the Lagrangian, that L is nothing but T minus V. So first we need to find out the kinetic energy of this pendulum. So kinetic energy, what do we know? Kinetic energy T is nothing but half into m into V square. So for here we have seen what is the value of V. V is nothing but L into d theta by dt. That means nothing but L theta dot. This is my V. So you use this equation, half m into L square theta dot square, because V is nothing but L theta dot. So V square will be L square theta dot square. Great. Now what will be the potential energy? Potential energy, obviously mg into h. So mg, and we are providing the height difference here, L minus L cos theta. So mgh. So this is my potential energy. So we are, once we have the kinetic energy and the potential energy, we can formulate the Lagrange. It's nothing but the kinetic energy minus the potential energy. So what that Lagrange look like? Lagrangian. So T already we have calculated, half m L square theta dot square, and also V we have calculated this quantity. So just use these two in your equation to get the Lagrangian. So the Lagrangian look like this. Say equation number 1. Now we can easily use that Lagrangian equation. What that Lagrangian equation say is nothing but d dt of, say if I want to write it, say it's simplify d dt of Lagrangian over your qk dot minus del L by del qk is equals to 0. Now here for this system, what is the generalized coordinate? Only we have only one coordinate, the theta. So that's why d dt of dou L by dou theta dot minus dou L by dou theta is equals to 0. Now just simplify this equation. Say d dt, now d theta dot, I want to write like this L. So here just open up this thing and simplify it. So d dt, now del by del theta dot. Now I can write the Lagrangian like this. Now here in Lagrangian, look at the Lagrangian over here. We have only one component associated with theta dot. So obviously derivative of this component will be 0, no meaning of writing that. So just write this thing here. So half into m into L square theta dot square plus we have theta del by del theta. So with respect to theta we have only this quantity minus mgl 1 minus cos theta. So minus and minus will become plus over here, right? So now simplify this equation. What we will left with the dt of like del theta of half ml square theta. So it will leave with ml square theta dot plus mgl sin theta is equals to 0. Now simplify this equation again. We'll get ml square theta double dot plus mgl sin theta is equals to 0. And further simplifying, we will get the equation of motion for the simple pendulum theta double dot plus g by l theta is equals to 0. Now, if we have this equation, we can easily calculate what will be the natural frequency of the system g by L. So what we have seen, like this equation of motion for the pendulum, we can derive it using equation that D'Alembert principle, using Newton's third law of motion, using that energy principle. Also, we have seen we can derive it using the Lagrangian equation, and this is very much useful. Here we have seen that we can easily derive it using the concept of kinetic and potential energy. Once for a system, for a complex system, where that step function and all these things are unknown, then we can easily use that Lagrangian equation or the Lagrangian approach to solve the dynamical properties of the system, or to formulate the equation of motion of that complex kind of system. So Lagrangian equation is very much important to, okay. So to use that Lagrangian equation, what we have seen, like we need to first formulate the Lagrangian, which is nothing but T minus V, that means the kinetic energy minus potential energy. Once we can find out these two quantities, we can use in a Lagrangian equation, and the Lagrangian equation says d dt of del L by del QK dot minus del L by del QK is equals to 0, where QK is nothing but your generalized coordinate of the system. So now you can see we have started from the generalized coordinate, and we are almost here with the Lagrangian equation where the generalized coordinate is sitting. Now, using that equation, let's solve another example, and then we will move to other topic. So here also similar kind of problem is here. A simple pendulum is shown in figure. Find out the kinetic energy of the pendulum in terms of generalized coordinate theta. Also find out the Lagrangian of the pendulum. So Lagrangian of the pendulum already we have, you know, formulate here the Lagrangian, right? Still, let solve here also. So obviously here they have given in terms of mass theta. Okay, everything is given. So this actually already we have solved it. So just go back and see it. Like what will be the value of just here? I'll show you. What will be the value of S? That means the displacement is L theta. What will be the value of velocity? It's nothing but L into theta dot. Now what we need to do, you need to formulate the T value. That means what will be the kinetic energy? The kinetic energy will come as half m into L square theta dot square, and the potential energy. Now if you rewrite it here, you will get the Lagrangian. For the system also we will have the Lagrangian same. Great. Now using that Lagrangian equation, okay, for now, do you have any kind of questions? Sorry, Nadal? Nandal.
Other? No.
Nandal. Okay. Okay, then let's quickly see few things regarding calculus of variation and Euler equation, and then we will solve few MCQ type of question, and then we will close our session. Okay, so let's go through some portion of calculus of variation. Like we have now idea of the action integral, about the first variation of the the Hamiltonian principle, which says that the first variation will be zero and all these things. Say for example, let's consider we have a functional. Functional, that means a function which contain different functions. Like here, f is a functional which is a function of y dot and x. Now for this functional, if I want to write the action integral will be from, say for example, for x1 to x2, I want to write down the action integral. So from x1 to x2, it will be f of y dot and x dx. Now how we can find out the value, that the optimum value of the function at any x star point here. So for example, I want to find out the optimal point x star, or the value of the function of x star. So obviously I need to look for maxima or minima. That means we need to differentiate this function with respect to x and equate to 0. So for this case, how we can solve this problem, or how we can deal with that. So for this type of problem, we actually consider a small variation uh, on that function and use the Taylor series expansion. So for example, here we have considered the small variation with the functional, so f x plus epsilon. Now we will expand this series using the Taylor series. So what we will have, f of x epsilon df by dx plus half of epsilon d square f by dx square. That means we are truncating the series up to the third term. Okay, here we have truncated. So we will have different higher order terms over here, but we are truncating the series over here. Now if we simplify it, what we will left with, f of x plus epsilon minus, that means f of x plus the small variation minus f of x is equals to nothing but epsilon df by dx plus half epsilon square df square by dx square. Now if we rewrite the term del f, that means the small variation is nothing but comes as this. Now look, if we want to uh, solve this function at x star point, we can easily do it. That means if we want to consider the stationarity of this thing, then we can easily calculate what will be the value of that delta f. It comes as epsilon square by 2 del square f by del x square. Now similarly, if we have different kind of function, we can expand this series based on these conditions, and we can do the needful. Like here, if we have you know from this example, we can understand this thing, how we can use that weak variation, and we can find out the Euler's equation, Euler first equation and Euler second equations. So here again we have 2 point A and B. So if for this system, if I want to define the action integral between these 2 point A and B, what will be that? The action integral I of y will be nothing but a to b f of y dot into x dx. Now if we assume that the action integral is linear, that means linearity, it will follow the rules of linearity. That means I of alpha into y, if you multiply the scalar, it will be alpha into that. If we have I of x plus y, it will become I of x plus I of y. That means if we have a linear action integral, then what we can do, we can propose some weak variation over this integral. Weak variation, this epsilon and eta we have considered, and this is also function of x. We have considered that weak variation over this. That means weak variation means, that means the function eta of x, that eta of x is such that it will be 0 at x equals to a and x equals to b. That means at this 2 point there will be zero variation, and over the path there may be some variation. We call it the weak variation. Now if I want to write down the variation del I, what will be that? That I of y plus with the variation, little variation eta minus I of y. Right? Now just uh, put all this expression and rewrite this like this f of, because it's a function. What is that y? I of y is nothing but it's a function of y dot and x. So we just write down that f of y plus the variation comma y dot plus the variation and x minus the f of y dot into x. Now what we will do, we will expand this part using the Taylor series, because we have seen it like how we are proceed with this kind of problem. We assume some small variation and then we expand it using the Taylor series, and we will get the final form. So now this term, if I want to expand it, f y plus that's variation comma y dot plus this minus y dot into x. So here on this side, if I want to expand this, f of y plus zeta n y dot plus zeta n dot into x, this not be, this will be zeta, not c. Okay, so what will be the function as per the Taylor series expansion? That will be nothing but the function plus that variation plus half of this, and we have truncated the series up to this order. So what we will have if we simplify this equation, this term, so we will left with the del I. Now just put all these terms in this equation here, in this equation number, if we want to identify this equation as equation number 1. So if we want to put all these things in equation number 1, what we will get? We will left with del I is equals to first part, which is associated with the variation, and then that means the linear part. One is the quadratic part, square term of the variation is there, and the remaining part of the equation. If we want to truncate it over here, we can truncate it, or we can consider the higher terms also. So from here we can see that my del I is actually depend on some linear function and some quadratic function, right? And at the very beginning we have assumed that my I of y is linear. So that means we will now work with that first part of the integral, that I of y, the linear integral part. Now the linear integral part, here we can see this is nothing but that part. Now take this part and satisfy the stationarity condition. That means the stationarity condition means, that means your first variation will be 0. That means I of y equals to 0. So take this part, I'm taking this part over here and equating it to 0. So if we simplify this, we will leave with this expression. Now further, this complete expression can also be simplified. Like if I consider only this part of this equation, I can expand it using the two function f1 and f2, or integration of uv rule. We can apply the integration of uv rule, and we will get it like this, the second part. Now complete the integration, you will left with this. Again, we know that the variation del I is equals to 0 for the stationarity condition. Now if we simplify the eta cannot be 0, so we will left with this equation del f by del x minus d dx of del f by del y dot is equals to 0, and that is called the first Euler equation. Very useful thing. When we will use that, we will see just a mathematical derivation you see. Now if we again take the first differential of this thing with respect to t, we will left with this final expression. I will not going step by step. If you go and watch the video of this instructor, he actually written it in pen and paper. You can easily see and you can correlate the thing. But finally, if we again solve it further, we will left with this equation. Now look at this equation on the other slide. If I take it to that slide, So what that expression says, like d dx of f minus y dot del f by del y is equals to del f by del x plus y dot del f by del y minus del f by del x del f by del y dot. Now here you can see this term is nothing but the first Euler equation what we have just derived, del f by del y minus del f by del x del f by del y dot. This is nothing but the first Euler equation 0. So this part will get 0, we'll left with this part only. So this will get 0, so we'll left with this part, d dx of f minus y dot del f by del x is equals to del f by del x. Now obviously del y by del y, if we have like we cannot establish any explicit dependence on f and x, then obviously dy dx equals to 0. So if dy dx is equals to 0, what we left with, we left with f minus y dot del f by del x is equals to constant, and this is called the second Euler equation. Okay, so this is the actually the basic part of the variational principle. You can see it. We have another parts like, can we get the Lagrangian equation from the D'Alembert principle? Yes, we can also get the Lagrangian equation from the D'Alembert principle, because we have just derived the Lagrangian equation from the Hamiltonian principle. Similarly, we can derive the Lagrangian equation from the D'Alembert principle. So today we will not go into this, like the derivation, the entire derivation I have added it. Like we need to start with the physical space and the virtual work done. Then we just need to solve this using the chain rule, and finally we will get the Lagrangian equation obviously from the D'Alembert principles. And also we have two more things like Hamiltonian and Hamiltonian canonical equation. Similar kind of thing, we need to formulate the Hamilton first, and we need to calculate the rest of the quantity as per the Hamiltonian. So we have few questions here, like what is Hamilton? Hamilton is nothing but uh, here like we need to solve this equation, and then we can we can answer this question. Like we need to have the concept of generalized momentum and all these things, but today we don't have any time to explain these things, so we will not go into these things. So we will quickly solve one example or two example which actually required to your for your assignments. Then we will wrap up this session. So let's quickly solve few MCQs from here, like which formula represent Hamilton's least action principle, where T and U represents the kinetic energy and the potential energy of the system. So obviously what I have seen, we have seen that del I should be equals to 0. That means the first variation should be 0. That means del of T1 to T2 T minus V or T minus U dt is equals to 0. That means the option B will be the correct answer. Now, how the second question says the total kinetic energy of a system, the total kinetic energy T is given. Calculate the terms of Lagrangian equation. Okay, the terms is already provided. Like we need to calculate d dt del T by del Q 1 dot minus del T by del Q1. So what will be that value? So obviously that value will be, if you integrate m by 6 Q1 square, so you will get the expression B as the first part. And for the second part, if we need to calculate d dt, you just need to do the integration. Please do it by yourself. Q2, so we just need to differentiate with respect to Q2. That means for the first part we only have this portion, and for the second we have only this two, and for the first part also we have this two, because we need to first differentiate with respect to Q1, then we need to differentiate with respect to Q2, minus again del T by del Q2 is equals to, you just need to perform these two differentiation and you will get the answer as B and D. Right? Right? Say d dt of del T into del Qi, del T into del Qi qi dot. So we have only these two terms only, qi dot, that means 2 into qi, and here q2 only, we will left with that q2. So obviously q1 double dot and q2 will be there. Great. Now we have another problem. Let a function f y dot and x, the action integral is given, the action integral I y is also given. It's x1 to x2 f of y dot into x dx. Now for di is equals to 0, find the first and second Euler equation. X is independent variable, k is constant. Great. So few times back we have derived these two equations. Precisely we have derived these two equations. Euler first and second equations. Here. This is the Euler's first equation, this is the Euler's second equations. So now go and choose the option correctly. So obviously, what will be the Euler's first and second equation? The Euler's first equation will be uh, that a df by dy dx of df by dy dot is equals to 0, and the Euler's second equation f minus y dot df by dy dot is constant. Here they have said k is constant. Either you can use c or k as constant, right? Now, we have left with another example, like let the Hamiltonian function is there where qk and pk are the generalized coordinate and generalized momentum. Find out the Hamiltonian canonical equation. Find out the Hamiltonian canonical equation. Okay, we need to express this with terms of generalized coordinate and generalized momentum. So we have like del h by del qk is minus p dot k, and we have another formula as del h by del pk is equals to q k dot. Here if you follow this lecture, you can find these two quantities over here. I will just show you here. Del h by del qk is nothing but minus p dot, and your del h by del pk is q dot. These two quantity as per your Hamiltonian canonical form. So you have two answers for this. So for now we will conclude this. We will further explain these things when we will uh, go into the module of continuous system. Then we will see again, we will formulate different equation of motions using Lagrangian and Lagrangian equation and try to solve them. So today what we covered, like we have understood the concept of generalized coordinate, generalized single degree of freedom system. We have also see how to solve problem using Rayleigh method if the shape function and the response quantity is given. Then we move to the uh, you know um, Euler's equations, and from Hamiltonian equation to we have derived the Lagrangian equation. We have solved few examples regarding the Lagrangian equation. Here we have seen that, and also we have solved different examples from the Rayleigh method. Okay then, if do you have any kind of questions, you can ask me, or we can conclude the session here. We will meet next day. Yeah, you are not audible. Want to say something, Nandal? Nandal. Nandalal. Nandalal. Nandalal, right? I'm pronouncing it rightly, right? Nandalal. Can you hear me? Okay. So, do you have any kind of questions, or we can conclude the session? Yeah, please. You are not audible actually.
You are not audible.
Yeah, tell me what you unmute yourself and tell me what you want to ask. Unmute yourself. You can unmute yourself and ask the question. We actually cannot hear you. I think you can rejoin.
Hello.
Yeah.
Sir, actually, what I was telling now. Now we are in the end of seventh week, sir.
Yes.
Okay, and sample questions now for the exam, final exam. What will be there? Whether it can be provided, sir?
No, sample question will not be provided, but the question will be similar to your assignments.
Oh, similar to assignment.
Similar to your assignments, and I will actually try to conduct one class after your 12 session, 12 week. Which kind of questions may come, like sample kind of questions. I will
Okay.
2 hours class.
Okay, sir. Okay, thank you, sir. Thank you.
Yeah, but for now, for the exam, you can like expect the question similar to your similar kind of questions. Still, I will conduct a 2 hour class dedicated to the questions which may come from your final exam, because it is important within that 2 or 3 hours you need to solve a lot of problems. Okay, so I will discuss about that in details on, I think, on 12 after 12 lecture. Okay.
Okay, sir. Okay, thank you, sir.
Okay. Thank you then. I will meet again on the next class.
Okay, thank you. Okay, bye bye. Have a nice day and nice weekend, sir.
Yeah, nice weekend, you people too, and have a nice assignments too. Thank you. Math something in the MATLAB.